Okay, we are ready to go move on to our next unit. So just to remind you what we have been doing over the last 2 months, we have been basically describing the motion of an object. We've been either describing it in words, using equations, using graphs. And so the words we've been using to describe the motion have been these three vector quantities here: displacement, which is a change in position; velocity, which is the rate at which position changes; and acceleration, which is the rate at which velocity changes. And the mathematical models we've been using have been graphs of motion, such as position versus time graph, velocity versus time graph, and acceleration versus time graph. And then we've been using these equations of motion. This is the position as a function of time equation. I've been nicknaming it the GPS equation. This is the velocity as a function of time equation. I gave it the nickname speedometer equation. And then these are two other versions of these two equations. So this is velocity without time, and this is change in position without acceleration, that we can use to do the following things. We could describe exactly how an object is moving at a specific moment in time, talk about how an object moved in the past, or predict how an object's going to move in the future. So that's what we've been working on. But now we need to focus in on not just describing the motion, but explaining why the objects are moving the way they are, or not moving the way they're not moving at all. So it's going to require us to analyze forces, energy, and momentum. But right now we're just going to focus in on forces because that's our next unit. Unit 4 is forces and Newton's laws of motion. So after this lecture, which is our introductory lecture to Unit 4, you should be able to define force, differentiate, which means tell the difference between a system or an object and its agents, identify forces acting on a system, draw a force diagram that models all the forces acting on a system, and identify the types of forces and the agents exerting those forces on a given system. So let's get started. So first off, what is a force? A force is basically a push or a pull. And now, if it doesn't have a special name for a force, you're just going to call it a force of push. So like me pushing on the door or pushing on my chair, it's just a normal push or pull. It doesn't mean have a special name, but we're going to define a couple of them that have special names. So again, a force is a push or a pull. The units that we measure forces are in newtons, and in another lesson we will define what a newton is. It is a vector quantity, so that means forces have magnitude and direction. How hard are you pushing or pulling? In which direction are you pushing or pulling? This makes a force a vector quantity. And so when we talk about analyzing forces, we have to define what object we're talking about. And we call the object of interest, or objects, because sometimes it's a cluster of objects, we call that our system. And anything that's not in our system can be a potential agent. So I have this animation here, and you see that there's an object, the box, being pushed or pulled by the people. So in this case, the object, the box, is our system. It's the thing that's getting pushed or pulled, and the two stick figures, the people, they are the agents. They're not part of the system. They're the thing or the things doing the pushing or pulling. All right? So only things external to a system can be an agent. A system cannot basically push or pull on itself. So I want you to try this as you're sitting there at your desk or in your bed, wherever you're watching this video. I want you to take your left hand and your right hand, and you're going to push on each other in front of you, sort of making like a meditation pose or a prayer pose. I'm not asking you to pray or meditate. I'm just asking you to put your two palm to palm together, and I want you to push as hard as you can on your left and your right hand. I'm doing it right now as well, and I'm not moving. Like there's nothing. I can keep pushing on. I can push harder, but nothing's happening. There's no movement of my body because I am internal to my hands are part of my system. They're internal to me. I cannot push on myself. Okay? But if you try now, place your feet firmly on the floor and push back on your chair. either your chair slides, my chair rolls here at home, but you are pushing down on the floor and the floor is pushing up on you. Those are two different things. You are the system, but the floor is pushing up on you. That's an agent pushing on you. And then you experience a net force. You accelerate in a specific direction. Okay, so it's super important that we keep track of what is the system and who are the agents. Okay, so when we actually represent all these different types of forces, we're going to want to be good at, we're going to have a lot of practice basically at drawing things called force diagrams. So when we represent forces, it's going to get kind of cumbersome to write everything out in words. So we're going to have this sort of labeling system. And this is our labeling system right here. A capital F just means that what we are identifying is a vector quantity known as a force. The first layer of subscripts is going to be the type of force, and we're going to abbreviate a force by a single letter. And then the second layer of subscripts are going to identify the object or the system first, and then the agent second. So the object that we're drawing the force diagram for, or the system, the thing that's getting pushed or pulled, and the agent is who is doing the pushing or pulling. And so that's how we're going to label forces. It's super important you remember this because on the A-level question on the test, you will lose points if you're not thorough with your labeling. All right, so let's go ahead and define our first force. The first force that we are going to be using almost all the time is pretty much all the time, is called the force of gravity. It's sometimes known as the weight. And we're going to represent that as capital F, representing vector quantity that is a force, and the lowercase g subscript means force of gravity, but it's a force of gravity unique to Earth. So we're going to narrowly define for now the force of gravity with capital F, little g. That's always going to represent the force of gravity on Earth. So it's the pull of the Earth on any object that has mass. Okay. Things that are external, the sun exerts a force of gravity on the Earth. The sun exerts a force of gravity on all the planets. The Earth exerts a force of gravity on the sun. The center of the galaxy exerts a force of gravity on everything that runs around it. Galaxies exert forces of gravity on other galaxies. That's also a gravitational force, but we're going to represent that differently, and we will learn a little bit more detail about that in our next unit, Unit 5. But for now, we're just going to narrowly talk about the force of gravity that the Earth has on any objects of mass that are in what's called its gravitational field. And we're always going to be capital F, lowercase g is the subscript. So again, it's the pull of the Earth on any object that has mass, also known as weight. When we draw this force, we are always going to draw it straight down to the center of the Earth, or on our paper, it's just going to go point straight down. Okay. And so there's this infamous or famous example of how Newton discovered the law of gravity, and it has to do with some apple falling off a tree and hitting him on the head. So let's do that. Let's draw a force diagram of this apple that's falling through the air. Okay, we've frozen it in time for a hot minute so that we can draw a force diagram of this falling apple. So right now, the only force acting on the apple is the force of gravity. We are ignoring any air resistance, plus the apple's not that far from the ground. Even if there was air resistance, it would be teeny tiny, be it a force. So this is Newton's apple, famous apple. So there's just one force. It's the force of gravity on the apple by the Earth. Because the apple is our system and the Earth is the agent pulling on the apple. That's a whole lot of stuff to do. You have to draw a picture of the apple, and then you got to write all the words out. So I'm going to show you what's called a free body diagram, which is a lot simpler and concise. So when we talk about a free body diagram, we mean draw the object or the system simply as a dot. So this dot represents that apple. And now we're just going to draw the forces and use our little subscripts. So this is a force down, blue arrow. It's a force of gravity on the apple by the Earth. That's so much less to write than the whole words. And so now that we have this sort of labeling system, you need to tell me what all your letters mean. So you have to provide a key or a legend for your little subscripts. So you're going to remind me that FG stands for force of gravity, that our object is the system, which is A for apple, and that any agents pushing or pulling on our system are basically right now just E for Earth, right? So force of gravity on the apple by the Earth. Why don't you give it a try? Oh, wait. Oh, I forgot. The forces aren't balanced. So there's only one force acting on it downward. If the forces were going to be balanced, there'd be another force upward, opposite direction, but same magnitude. But right now there's just one force, so this is called unbalanced, so that the net force is going to be a non-zero number. It's not zero. Okay, so here's what you're going to do. It's your turn. You're going to draw a force diagram of the falling pencil or falling rock. You get to decide which one. So please draw a force diagram of the pencil falling through the air or a rock falling through the air, and pause the video so that you can try it, and then push play again to check your work. Okay, so let's see how you did drawing the force diagram of either the pencil or rock. Since I'm not sure which one you did, I'm going to just say S for system. And so I have just a dot representing the pencil or the rock, force of gravity on the system by the earth. And there's only one force down, which is the force of gravity. How'd you do? I hope you got it right. If not, if you did the pencil, now do the rock. If you did the rock, now do the pencil, and then check your work again. All right, that's one force. Let's move on to our next kind of force. Normal force is a type of support force, and we're going to write F with a lowercase subscript n. And this means whenever you draw this, I know that you mean normal force. It's a force that acts perpendicularly between two surfaces in contact with each other. For example, the floor pushing up on you when you stand on it. So here's my little Bitmoji. I'm standing on the floor, and so we're going to draw a force diagram, and you're going to see what it looks like. But basically, the floor is pushing up on me while the earth is pulling down on me. So I'm going to do a free body diagram. So this little red dot represents me. Here's our first force. We're always going to draw a force of gravity on me by the earth straight down. And so I'm standing in place. I'm not floating up in the air, and I'm not sinking down to the ground. So there must be a balancing force to this force of gravity. And there is. There is this normal force on me by the floor, which I'm abbreviating FL. So here is my key. Fg equals force of gravity. Fn represents normal force. My object or my system is represented by the letter M, which really just means me. And who's pushing or pulling on me? The E for earth and FL for floor. Okay? One more thing. Because I'm not floating up or sinking down, because these forces are balanced, I'm going to put these little congruency marks. So when we say forces are balanced, we're saying when we add up all the forces acting on the system, they equal zero. Net force equals zero means the same thing as balanced forces. Okay, your turn. So now you're going to draw a picture of this Halloween decoration. By the way, that's a picture of a Halloween decoration in front of my house. I just bought them, so I'm kind of proud of them. Anyways, you're going to draw a force diagram of the ghost decoration, okay? The ghost decoration is just hanging out there. So please draw a force diagram of the ghost in the ghost decoration, and pause the video to try it out, and then come back and check your work. Okay, how do you think you did? Let's check your work. I'm going to show you what I did. I have the dot, red dot represents the ghost, and we have a force of gravity on the ghost by the earth, and a normal force on the ghost by the ground that he's sitting on. And so because the ghost is not floating up in the air or sinking into the ground, these two force congruency marks means the forces are balanced. How did we do? Thumbs up, we did great. If you had a hard time with that, you could practice drawing a force diagram of the pumpkin right next to them. All right, let's go on to our next force. So normal force is a type of support force. Again, it's usually reserved for like solid objects. So like the ground, the grass, walking on, you're standing on something, you're sitting on something. Usually that's just what we talk about. Nothing, that's what I'm talking about. Sorry. Next one. Buoyant force is almost like a support force, but it's not exactly. We're just going to say F, capital F with lowercase b. Buoyant force is a force that a fluid like water exerts on an object immersed in it. So it could be an object that's like floating on top of this fluid like water, or sinking a little bit in the water, but there's still a buoyant force, or completely sunk. There's going to be a buoyant force. So that's why I say it's almost like a support force, but it isn't always a support force. And so we will go in more detail second semester on buoyant forces, because if you remember, our second semester project is a cardboard boat, and we're going to go into more detail about buoyant forces so that we can do some calculations and build a boat that we can row in the pool. Okay, but moving on about just basically buoyant force. So let's draw a force diagram of me and the boat floating in the water. So there's a force of gravity on me and the boat by the earth, pulling us down. And there's a buoyant force on me and the boat by the water. And so I decided to just leave M as the object, but the M stands for me and the boat. So we've got a force of gravity and a buoyant force acting on me. So the earth is the agent that's exerting a force of gravity on me and the boat, and the water is the agent that's exerting a buoyant force on me and the boat. All right, and remember these two congruency marks, since I'm floating, I'm not sinking down or floating up in the air. We're caught at a moment where it's in equilibrium. These forces are balanced. So the forces are balanced. Now I want you to try it. Try drawing a force diagram of the floating rubber ducky. Please pause the video so you can give it a try. All right, welcome back. How did you do? Did you have a force of gravity on the duck by the earth and a buoyant force on the duck by the water? The gravity force is straight down and the buoyant force is straight up. And did you mark them that they're equal in magnitude because the forces are balanced here? So it's almost exactly the same force diagram. You just changed the system. Okay. I want you to notice that I'm going to try to stick to this color coding system that we have with this first set of notes. Whenever I draw a force of gravity, I'm going to be using a blue marker or blue arrow, color arrows. And the buoyant force is going to be green color arrows. So we're going to call that buoyant force. Okay, ready to move on? We're going to look at our next force. Force of friction. This is known as a resistance force. And we're going to say capital F is the force. It says that this vector quantity is a force. And then the lowercase f means it's the force of friction. So a force of friction is a force exerted by a surface that opposes the direction of motion of an object moving across it. Okay, it's going to oppose the direction of motion. So let's draw a force diagram of me on the skateboard with apparently a raccoon. We're moving in this direction. So the dot represents the system. So the force of gravity on the system by the earth. There's a normal force on the system by the ground. And since we're moving to the right, the force opposes the direction of motion, then our force of friction should be to the left. And so that's why we're trying a force of friction on the system by the ground. So look, the ground is pointing in two directions. That happens. The ground can exert forces in all different directions. In this case, it's flowing up for normal, and to the right is going to be for friction. And these two forces are balanced, but we have this one force of friction that doesn't have a balancing force on the right there. So then we would say the forces are not balanced because not every force has a partner. So here we go. The force of gravity is Fg. Fn means normal force. Ff stands for friction. The object is S for skateboard plus the riders. And who's pushing or pulling on the system? The earth and the ground. Okay? All right, your turn. This time, I would like you to draw a force diagram of the sliding penguin. So the penguin slips on the banana peel and slides across the ice there. So that means see how it's sliding down? That means there definitely is a force of friction there. All right, so pause the video and give it a shot and then come back and check how you did. All right, how'd you do? So I'm going to draw this red dot to represent the penguin. Then there's a force of gravity on the system by the earth, a force normal on the system by the ground or the ice, and there's a force of friction on the system by the ground or the ice. I should have called that I for ice. But it looks almost the same as this one, but notice how the penguin's moving to the left, so the force of friction that we're drawing on the penguin is to the right. The normal forces and gravity are equal in magnitude, so they balance each other. But again, we have this one force of friction that doesn't have a balancing force pointing to the left, and so it's not a balanced force situation. So there's a net force that is not equal to 0 acting on our system. Okay, I think we're ready for our next force. Here we go. Force of drag. Force of drag. So it's a force of friction with a fluid. So see, now this is our second force with the fluid. There's buoyant force, and that's more like a support, kind of like a support force, but the object has to be like moving vertically through the fluid. Here, the force of friction, the object is going across the surface. So the force of friction with the fluid, or the resistance of motion of an object through a fluid, like air resistance or water resistance. So if you are like completely underwater and you're swimming underwater, you will experience a force of drag that acts opposite the direction you're moving. Okay? All right. So let's draw a force diagram of the same penguin that was sliding on the ice. Now he's jet skiing. He's a very active penguin. Okay, sorry. So we're going to represent the dot is the penguin and the jet ski together. They're going to be our whole system. So then this is force of gravity on the penguin by the earth, force of buoyancy on the penguin by the water, force of drag on the penguin by the water. All right. So again, this is an unbalanced force situation. The buoyant force and the gravity might be balanced. They might be equal to each other, but there's this unbalanced drag force here. So let me see, did I fix it? Oh, I did have a good, I wasn't sure if I fixed the key, sorry. So Fg is force of gravity, Fb is buoyant force, Fd is drag. The object P stands for the penguin and the jet ski. And who's pushing or pulling on the penguin and jet ski? The earth is pulling it down, and the water is pushing up and opposing the direction of motion. So in this case, to the left. So this is a not balanced forces situation. And so why don't you give a different one a try? This one's going to be completely different. So I'm testing your understanding of the force of drag. So your turn. You're going to draw a force diagram of a feather falling with air resistance. So it's not in free fall. It's falling with air resistance. So please pause the video and give this a try to draw the force diagram of the feather as it falls to the ground. All right, I'm back. How'd you do? All right, remember, it opposes the direction of motion. So let's see. Do you have a force of gravity on the feather by the earth? And do you have a drag force on the feather by the air? Right? I drew them that they're congruent because I'm imagining that the feather sort of moved at a constant velocity towards the ground. I would say you don't necessarily have to have these congruency marks. I kind of wish that I remembered to remove them, but now that they're here and I don't want to have to re-record this video all over again, I'm going to say that in this case, the feather is falling with a constant velocity, although it doesn't look like it is. So these don't always have to be congruent, okay? I think focus in on that you got gravity and drag, and that drag was up because gravity was down because the feather was obviously moving in the downward direction. Oakley dokley, we're moving on. Force of tension is a pull through a rope, wire, cord, string, muscles, or chain. So it's F with a lowercase t. And so we're going to draw a force diagram of me on a swing. So this red dot represents me and the swing chair probably. I'm going to pretend that me and this little wooden board that I'm sitting on, that's our system. And the only things are the rope is not part of the system and the earth is not part of the system. So we've got a force of gravity on the system by the earth, a force of tension, because this is a rope, on the swing from the left, and a force of tension on the string from the right. Because they're two separate ropes, I'm going to have a left force and a right force. Okay, so Fg for force of gravity, Ft for force of tension. The system is me and the swing seat. But notice that there are now three agents: the earth, the left rope, and the right rope. Okay, so now I want you to try it yourself. This time you're going to draw a force diagram of Kevin hanging from the tassel. See his tassel stuck to the light there. We're going to call it his tassel on his hat. Looks probably like a light socket, but we're going to pretend that's his tassel on his hat. So pause the video and draw a force diagram of Kevin hanging from the tassel on his hat. All right, welcome back. How'd you do? Did you get force of gravity on Kevin by the earth and force of tension on Kevin by the tassel? The tassel's pulling him up. All right. One more piece of information here. The forces are balanced here because there's an upward force here and a downward force here. So this means that the magnitude of this force is equal to the magnitude of this force. So the forces are balanced. In this moment here, I would say you could say the forces are balanced as well. The force of tension on the left and the force of tension on the right, they're both going to be equal in magnitude, but they're pointing in the same direction. It would be balanced if you added these two and they equal the force of gravity. So we're going to pretend that it is, and so that I only draw congruency marks though when the forces are equal in magnitude. Equal in magnitude, equal in magnitude. In this instant, it's definitely clear that these forces are balanced. In this instance here with the swing, we would have to know the magnitudes of these two orange vectors and see if they equal the blue vector, and then that would tell you if the forces are balanced. So I would say if this is at the bottom of her swing, then the forces are definitely balanced. More later, but that's why we reserve those congruency marks to say that they're the same magnitude. Okay, we just got I think we got three more. Three more. You're doing great. All right, elastic force, F lowercase e for elastic. Sometimes I might call it a spring force. Sometimes when I say EL for elastic force, I'm going to do FE. It's a push or pull that results when an object is deformed and can return back to its original shape. If we were doing this in class, I'd show you a spring. I can pull a spring and it'll snap back to its original shape. Or a rubber band, I'll pull a rubber band and it snaps back to its original shape. Or you got a Nerf ball, you squish that Nerf ball and it pushes back, returns back to its original shape. Examples of things that can exert elastic forces: springs, trampolines, rubber bands, bungee cords, anything that's stretchy and will go back, right? So yoga pants, they can stretch and go back to the original shape. I'm not sure what else. Okay, so we're going to draw a force diagram of me jumping with a bungee cord. We're going to pretend that's not drawn the way it is, that the bungee cord is stretching or stretched. So there's a force of gravity on me by the earth. There's an elastic force on me by the cord. And so there's force of gravity, an elastic force. The object is me. And who's pushing and pulling on me? The earth is pulling me down and the bungee cord is pulling me up. I would like to say I would never bungee jump in real life because I'm too scared. I am kind of scared of heights. Anyways, the force on the cord could be called a tension force, right? Some people want to call it a tension force. I mean, it could be, but because the bungee cord is elastic, that's more the reason why I'm moving the way I am, is because we've got this elastic force. Because if it was just a rope, I might bounce around, but I wouldn't go back up as high as if it wasn't a bungee cord. Okay, so bungee cords, we're going to stick to elastic forces. All right, your turn. You're going to draw a force diagram of this weight here, this little brassy looking cylinder, and a force diagram of the weight bobbing up and down from the spring. All right, so you're going to draw the force diagram of that. This one's a little tougher. Well, not really, but you might get a little confused. Just draw the forces acting on the little weight. Pause the video. All right, welcome back. You only had to draw two forces on here. There was a force of gravity on the mass by the earth, and there's a force elastic on the mass by the, that should have been C for spring. It should have been S for spring, but it means the coil. That's what it is, by the coil, which is a spring. All right. I didn't put any congruency marks because, as you can see, at some point it's falling down and other points it's falling up. And that's because we will learn second semester that the elastic force on a spring or a rubber band is not constant. It's actually related to the amount of stretch in the spring. Okay, now we have two more. We're almost done. The other two forces, last slide. The other two forces that you may encounter are electrostatic force. Oh, almost looks like the previous one, but it's Fe minus. It's a push or pull between charged objects that aren't moving. Magnetic force is F with a capital B. Remember, we had buoyant force with lowercase b. Magnetic force is a push or pull between moving charged objects. All you need to know for now is that when we talk about forces between electrons and protons, electrons with each other, protons with each other, then we're talking about electrostatic force. When there's a magnet involved, you're going to call that magnetic force. There's a lot more to it than that, but as far as we're concerned, that's all we need to know. Okay, great. So now you know all the special kinds of forces that we're going to be dealing with that have forces that have special names. Anything else, If it doesn't fit one of these categories, then it doesn't need to have a special name. You're just going to call it a force of push or a force of pull, and that would be capital F with a lowercase p as a subscript. Sometimes they call it force applied, and they say capital F with a lowercase a pp, to show you that's just a generic force. There's no special name for it. Okay? All right. Well, I'm looking forward. We're going to have fun next class doing a fun activity. Bye.